Representation Learning in Lower Dimensions and Spectral Methods in Machine Learning. I'm Vishnu Pendyala. I'm the chair of the Santa Clara Valley chapter of IEEE Computer Society, and I'm also the speaker for today. Uh, so this is an interesting topic that we have for today. Thanks for joining. And we all know that data often has a hidden structure, right? We want to discover and extract meaningful insights from this hidden structure in high dimensional spaces. Data typically is in high dimensions. The talk for today will require some basic knowledge of linear algebra, probability distributions, and a little bit of machine learning concepts will also help. So those are the prerequisites. Like I mentioned, the purpose is of this talk is to uncover the hidden structure of data and extract meaningful information or insights from this hidden structure. So here's an example. On the left-hand side, you have a table of data. So each column is a dimension or a feature. So the question is, which one of these reveal the hidden structure? So left-hand side, you have a table of rows and columns, each column being the dimension. Each row is a vector of multiple features. And each of these rows can be represented as a point in space, vector space, like on the right-hand side. The answer is obvious, actually, but I still wanted to pose this question. So the hidden structure is more visible when you visualize it in 2 dimensions rather than as a table of more than 10 dimensions, right? So representation learning in lower dimensions maps data points into a lower dimensional space and at the same time preserves key information of the data. So it projects data into important or essential latent features or hidden features, which can help with visualization, data understanding, and gaining insights, right? So a couple of weeks back, I presented a paper using the techniques to be discussed in this talk at a reputed conference in its 10th year. And the paper actually won the Best Paper Award. So this is a very useful set of techniques that we'll be talking about today. I'll share the details of the paper towards the end of the talk, but I just wanted to raise your curiosity. So the idea, once again, is to take this kind of information on the left-hand side in the form of a table with multiple columns which represent the dimensions. See, a vector of numbers is a vector in a vector space, right? Which is a point with magnitude and direction. So each of these rows is a point with magnitude and direction. We can uncover the hidden structure when we represent the data on the left-hand side in lower dimensional space for better visualization. So that is the key idea here. So why do we even learn representations in lower dimensions? I already gave you some motivation for that, but let us uncover more. So first is to visualize the hidden structure like we talked earlier. So typical visualizations work best when the data points are projected onto a 2-dimensional or a 3-dimensional space. And then if you're familiar with machine learning, there's something called curse of dimensionality. In case you don't know, I'll still discuss it after a couple of slides. More dimensions will make it hard to deal with data, and reducing the dimensions can simplify the data and make it more manageable. And then computational efficiency, right? The more the number of columns, the difficulties in terms of computing with those data, with that data. So reducing dimensions will make the training faster, and the inference times will also go down. There's another major problem with machine learning called overfitting. In high dimensional spaces, because of the sparsity of data, models may find complex decision boundaries to fit the training data precisely. So that is the idea of overfitting. Overfitting has some serious problems. In a different video, webinar available on YouTube and elsewhere, I mentioned how overfitting can cause tools like ChatGPT to memorize some of the training data. Some of the sensitive data could also be memorized, and it will lead to privacy concerns. So overfitting is a serious problem, and reducing dimensions will result in smoother decision boundaries and lower overfitting. And another great advantage of representing data in lower dimensions is making the data more interpretable, right? So we can draw conclusions from data. We can interpret the data and then make some conclusions from the data. In fact, the first and the last point, this point and the first point, helped in the work that I presented at the recent conference. So these are visualization and interpreting the data play a vital role in drawing insights. So there are more reasons. So another is reducing dimensions would also cause noise to be reduced, because when you drop dimensions, which are features, dimension, feature, column in a table, these are all used synonymously. They mean the same. So irrelevant feature and correlated features don't add much value. So when you drop those features, the noise will also be reduced. So that's one advantage of learning representations in lower dimensions. And reducing dimensions will obviously lead to more efficient and effective models. It will also improve the performance of the model. I'll explain this a little bit in more detail in a subsequent slide. Anomalies or outliers become apparent in lower, when you visualize data, outliers will become apparent in lower dimensional spaces. And it makes it easy for clustering and classification algorithms when the dimensions are reduced. I'll elaborate this also in the next slide, next few slides. And then the other great advantage of reducing dimensions is in form of compression of data. As we'll see later, images can be compressed using an algorithm called principal component analysis, which is which comprises the most of this talk. So when you compress the data, it helps in efficient storage and retrieval. So those are some more reasons for learning representations in lower dimensions. It is a well-known fact that training data needs grow exponentially with dimensions. So the more number of dimensions, the more data you need. So if you have more columns in the table of the data set, then you also need more rows in the data set. for machine learning to work well. So therefore, learning in high dimensions is intractable. So the calculations involved in searching for patterns and optimizing parameters will scale drastically with the number of features, with the number of columns in the table. It is almost impractical to train complex models on large data sets for that reason. The other major point with large dimensions is distances become less meaningful. So here's a paper published in 2019. And the blue dots are the mean of the distances between the points. So basically, the pairwise distances between the points are kind of normally distributed because we know central limit theorem. A lot of data is normally distributed. So we can think of the distances as distributed normally as well. And on the right-hand side, you see this plot where the blue dots denote the mean of the distances, pairwise distances between the points. The x-axis is the number of dimensions and the y-axis is the mean. And as it is understandable, as the number of dimensions increase, the mean of the distances will also increase. So that is quite intuitive. But what is interesting is the red dots. The red dots represent the variance. As you can see, as the variance, as the number of dimensions tends to infinity, the variance goes down to 0. So what does that mean? The variance of the distances. So that means most of the distances are pretty much similar, right? If on the left-hand side, you can look at the normal distributions for these distances for various dimensions. So when n is equal to 2, I think n is equal to 2 represents this blue normal distribution. The variance is quite substantial. But as the number of dimensions increase to 50, you can see that the normal distribution has peaked and the distance or the variance of the curve has reduced. So the variance is basically the distance between this and this kind of, right, in a normal curve. So as you can see, the variance as when the number of dimensions increases from 2 to 50, drastically decreases. And it is easily understandable that when the number of dimensions tends to infinity, the variance tends to 0. So what does that mean? That means that data becomes sparser and sparser, number one. The distances do not make much sense. And the number of regions in the feature space will grow exponentially, right? Because the regions would have just 1 or 2 points in them, and they would grow exponentially. Typically, density of the points and the distance between points play a very important role in many machine learning methods like clustering, classification, and other analysis. So these essential concepts of density and distance become less meaningful with more number of dimensions. So that also is a problem with high dimensions. And this is an interesting paper published by Jeffrey Hughes. So the phenomenon is named after him, Hughes phenomenon. This paper was published in 1968. And what it says is that the classification accuracy initially increases with dimensionality. So the x-axis is again the number of dimensions, and y-axis is the accuracy of the model, performance of the model in terms of accuracy. And as you can see, the classification accuracy increases initially with the number of dimensions, but then declines beyond a certain point. So, so reducing the dimensionality helps to eliminate irrelevant features, reduce noise, and also improve performance. And it also makes computation efficient. The time and space required in data mining gets reduced also. So that's advantage of reducing dimensions. So there are many methods, as we will see later, there are many methods to reduce dimensions. This principal component analysis is just one. In fact, you can reduce dimensions not explicitly also. For instance, in supervised learning where you construct decision trees, you can start pruning the decision tree to remove some of the features. Similarly, regularization. Some of the regularization schemes like the L1 regularization, if you know a little bit of machine learning, helps reduce dimensions, remove some of the irrelevant dimensions. There's a statistical method called ANOVA, which also helps with reducing dimensions. So the point is that there are many methods, but PCA is probably one of the most often used. So you can consider principal component analysis as a data summarization techniques. So first point to note is that it does not require any labels. So it is a completely unsupervised machine learning, no labels required. And so the idea is that the data with many features are condensed or abstracted into fewer principal components, component, feature, column, dimension. These are all used synonymously, they mean the same. So as you can see from the figure, we have the original data with n columns and m columns and n rows. That's the data set D. Now, the goal of principal component analysis is to reduce some of the columns. So the number of columns in the resulting data set will be k, which is less than m, and but the number of rows will remain the same. So it's only the dimensions which get reduced, not the number of data items. So obviously, we need some special techniques to do this. Any ideas on how we can reduce the number of columns? So one great analogy is on the right-hand side, that's weight loss, right? So when a person loses weight, he or she typically does not lose height, right? It's only the weight loss. So same thing with the data set. The number of rows will remain the same, but the number of columns will reduce. So one question. So we all know staple food varies from region to region, right? Like in Asia and South India, the staple food is rice. North India, it is wheat. In US, it is potato. In Hawaii, I think it is taro root. So why are all these foods considered staple food? The reason is, I'll probably not wait for answers in the interest of time because I have a lot of material to cover. But I'll keep on asking you questions and feel free to ask me questions as well. So the latent factor in these foods is the carbohydrates. If you know the food pyramid, it tells you that we need to consume more carbohydrates and less proteins and less fats and things like that, right? So, so rice, wheat, potato, taro root, these are all the staple food because of a latent factor hidden in these foods called carbohydrates. So if you go to a dietitian for weight loss, typically what happens is the dietitian asks you for your food habits, like you tell them that your breakfast comprises of bagels, cereal, or donuts, or whatever it is. So those are the original features. The original features of your diet are bagels, cereal, donuts, whatever it is. So those are the original features. And then the dietitian comes up with a plan. based on your original features. The dietitian comes up with a plan. And the diet plan does not include these original features. Instead, it includes synthetic features, imaginary, hidden features like protein, carbohydrates, fat, fiber, and things like that. So the dietitian would say, take this much carbohydrates in the morning, take this much fat in the morning, in the afternoon, consume this much protein, and so on and so forth. So these are synthetic features, like these are the protein, carbohydrates are synthetic because you cannot see them. They're imaginary. They're man-made, right? The concept of protein is man-made. We discovered it by research. The food scientists discovered them by research. So these are synthetic features. So from original features like bagel, cereal, eggs, and lentil soup and things like that, you come up with a combination of synthetic features, protein, carbohydrates, fats, and so on and so forth. So the goal of this diet plan is to lose extraneous weight, but not the important constituents. We want to lose weight, not the nutrients in our body, right? So the same thing applies to the data set. So we want to lose extraneous information from this left-hand side data set D to come up with a new data set X, right? So there's always this trade-off between effectiveness of representation and loss of information. We don't want to lose essential information. We want to, just like with weight loss, we don't want to lose essential nutrients and the essential composition of our body. Same thing with the data set. We don't want to lose essential information from the data. We want to retain the essential information, but at the same time, reduce extraneous information. So overdoing the dimensionality reduction will lead to loss of important and necessary information, just like overdoing weight loss will result in loss of important and necessary information, right? So if you lose essential constituents of your body, then we will lose some vitamins, or vitamin count will go down. A lot of essential substances will go down in our body, which is not desirable because it will lead to a lot of problems down the line. So that's the analogy for dimensionality reduction. So another intuition is, so a lot of happenings in the real world, like movies are shot in 3 dimensions, but we watch the movie in 2 dimensions without much loss of information, even when dropping the 3rd dimension, right? A lot of stuff in our day-to-day lives is extraneous. So for instance, another instance is we listen to music when working, but when we need to focus, we drop the music dimension without foregoing much, right? So when we want to make time, we try to forego some of the extraneous activities in our life to get more time, right? So this is a common concept, which is applied to data sets as well. So another example is the surveys that we typically do in a class or elsewhere. So the 3 questions: everyone in my team contributes to my learning, my team provides great insights during discussions, each team member creates a positive environment. All these 3 questions can be replaced by one single question. My team generates great synergy. So there's a lot of redundancy in the first 3 questions, but the latent intent is what is captured in the this question, right? So we are interested in discovering the latent intent in data similarly, right? So there's something called Prezi writing. You would have done it in your high school days, right? In Prezi writing, what we do is we condense the writing. We condense the information given to us into fewer sentences. So that's the idea of pre-writing. So that's something very similar to what we are doing in PCA and other dimensionality reduction techniques. So let us understand how we can do this. So to introduce that, I want to give you an example. So I will show you 4 plots. The x-axis contains the scores obtained in a course. So last semester I taught these 2 courses. There are 245, which is machine learning, and there are 228, which is big data. The x-axis is machine learning course scores and obtained by a student, and y-axis is a 228 scores. Each of these dots is a student. So the student obtained some score in 245 and some other score in 228. So these are all scores. So this is the first scenario. And how do you interpret the first scenario? So the first scenario indicates that most students got more or less the same scores in 228. The y-axis is more or less the same for everyone, but they vary heavily in 245. The machine learning course, students performed differently, quite differently, right? So the x-axis varied a lot, but the y-axis pretty much similar. So that is the first scenario. The second scenario is the other way around. Most students got more or less the same scores in 245, the x-axis, but they varied a lot in their 228 scores. Scenario 3, students got more or less the same scores in both 228 and 245, but the students do vary in their respective scores. So there is some variation of the scores of the students, but their scores, each student scored more or less similar in both the courses. So that's what is scenario 3. And scenario 4, students getting low in one, but high in other, consistently, right? So some students scored better in 245, but they scored poorly in 228, and vice versa. So which of these 4 plots is most likely, right? The answer is quite intuitive. The answer is scenario 3, because students who do well in one subject are likely to do well in the other subject also. These are the studious students who put in a lot of extra efforts and all that. And students who take it easy would of course not do well in both subjects. So probably scenario 3 is the most likely scenario. So what does the story tell you? The story tells you that correlation gives very interesting insights, right? The correlation or the covariance tells you a lot of story about the students. Now here's an interesting scenario. So after the semester, I get a lot of requests from students requesting for applying for research assistantships. So students say, I took your course, and reveal only the grade that's the best between the two. They don't tell, I mean, some students are like that. I cannot generalize, but some students say, I took your course and got A grade in that course without revealing that they got a B minus in the other score. But suppose I know this distribution from the last slide, how the data of the class distribution is. I know that, for instance, in scenario 1, students scored pretty much the same in 228, but vary a lot in 245. So I know those kind of trends. So if I know only one subject's grade, what would that subject be in scenario 1? So which subject would I prefer? to know the score about. Obviously 245, the x-axis, because that's where the students varied the most. I would like to choose students who scored very well in 245. All right. This is just a hypothetical example to explain a very important concept. So I just go by the axis on which the students varied the most, the x-axis. That is scenario 1. So data 245 is what I'll base my decision on. Because data 228, pretty much everyone got similar scores. So that's why I choose data 245. Now for scenario 2, I will choose 228 because that's where the students varied the most. Data 245, the students scored pretty much the same. Now scenario 3, I'll still go with the variance. If you have observed carefully, I've been going with the direction of the variance. So the direction of the variance was this in scenario 1, vertical in scenario 2, and in scenario 3 it is this slanted. So I'll still go with the direction of the variance, right? And how about scenario 4? Scenario 4, I cannot depend on either as a general rule. I mean, for a particular student, yes, I know, but um, uh, um, but given I don't know the particular student scores, assume that I don't know the particular student scores, I just know the general trend. I know that students who performed well in 245 did not perform well in 228 and vice versa. So when I know only that, I would not depend on either. Instead, I will try to extract latent information. So maybe an interview or things like that. So what do we conclude from all this? So what we conclude is that for our decision to choose a student for a particular position, what matters is the variance of how the data or about the students vary, right? So variance is a very key concept in understanding data, right? So that is what I wanted to drive home. It is the variance that matters. So another analogy, we all know caricatures. So who is this? I'm pretty sure you will all agree that this is the caricature of George W. Bush, right? So obviously this is not an exact representation. But still we know that it is George W. Bush. How do we know? We know because the caricature captured the maximum variance. The caricature captured the principal components just enough to serve the purpose. So, so George Bush obviously varies from the remaining people in his probably nose, the ears, and a wide upper lip. So those are the features where he varies the most from other people. The other things are pretty much not too distinguishable. So this is where the George Bush varies the most, the ears, the nose, and things like that. So what helped us recognize George Bush is the variance that the caricature captured. So cartoonists can identify where the information is varying the most, the latent features. In fact, it is said that creative artists can see what no one else can see. So there's a saying in my native language, which roughly translates to, a poet can see where even the sun cannot see. See, sunlight goes everywhere, right? But it is said that the poets can see where even the sunlight cannot reach. So that is the strength of creative artists. Cartoonists can see what others cannot see. And one other interesting point from this analogy is that the features, the nose, the long ears, are synthetic. They're imaginary. Uh, George Bush obviously does not have this long ears or this long nose. These are all synthetic. These are all imagination of the cartoonist, right? So generating synthetic features from original features is the creative work of artists in case of caricature, and creative work of algorithms like principal component analysis for data sets, right? So the analogy, so principal component analysis can be compared with caricature drawing, right? The right side is obviously not the true image of Barack Obama, but we are still able to correctly identify because the caricature focused on the oddities, where the person varies most from the other people. In this case, Obama's cheekbones and teeth seem to be where he varies the most. So the focus is on those. Similarly, PCA captures the directions where the data varies the most. So if you see the left side top figure here, the data is varying the most in this direction, where the cursor is moving, and less in this direction, right? It varies very little in this direction or in this direction. Those are the original features are vertical and horizontal. But the synthetic features synthetic dimensions are in this direction and this direction. So that is exactly what principal component analysis does. So then the next question is, how do we capture the oddities or unique variations in the data set? So data is still assumed to be identical and independently distributed. So they are still, they're all still yummy donuts, but they do vary, like in this picture. The donuts vary in their color and things like that, right? So data still varies, but they're identically distributed. Now, how do we capture the essence of a data set? So data set looks like a matrix, right? Now, how do you capture the juice or the essence of a matrix? So the answer is using eigenvectors. But the eigenvectors are not computed directly from the data set. There's an additional step that needs to be done. And what is that additional step? It is variance. Remember, variance plays a very big role in data. So we compute the covariance matrix from the data set, and then we generate the eigenvectors for this covariance matrix. And that's what gives us the principal components. So those are the key ideas. So principal component analysis is a linear technique. So what we are essentially doing is trying to project the points in the vector space, the rows in the data set, onto a hyperplane. We are assuming that the points can be projected to a plane, not a surface, not a curved surface. We are assuming that the data can be projected onto a plane. So it's a linear technique. And in spite of being a linear technique with that kind of limitation, it is the most popular technique in dimensionality reduction. So it originated in this paper in 1901, which is how many years old? 23 years old. Sorry, to 1023 years old, right? Or 123 years old, sorry, what am I? So it is 123 years old paper, authored by this person called Pearson. Does that ring a bell? Does the name Pearson ring a bell? It should, because this is the same person who gave us the correlation coefficient, Pearson's correlation coefficient. So these are all related concepts: PCA, correlation, covariance. These are all related, and obviously Pearson has been working on these areas. And correlation is linear, so it assumes the algorithm assumes that the relationships among the features are linear. So of course, 1901, the idea actually originated in 1901, but later on it was improved in 1933 and subsequent years. So a great improvement came in 1933 when Hotterling came up with this concept of analysis of a complex complex of statistical variables into principal components. So Hotterling's work is widely recognized as a foundational work in principal component analysis. But you should remember one thing: it applies only when features depend on each other. So ideally, we expect the data to be IID, like I mentioned in the previous slide, independent and identically distributed, but that independence is sometimes not present. In fact, most often is not present. The data is somewhat dependent. The columns are somewhat dependent on each other. The features are somewhat dependent on each other. So, and PCA tries to exploit that dependence. So this PCA algorithm is applicable only when features depend on each other. It is not applicable when features are completely independent, like assumed in naive Bayes, right? So there should be some amount of dependence among the features, among the columns. So that's the other important point. Now, so there are many variations and improvements of PCA since 1901. And the first application came in 1954. This was objective method for the classification of vegetation. So we are now, it was used for botany actually. This paper introduced the concept of factor analysis. So factor, feature, dimension, component, what else? So all these are used interchangeably. They all mean the same thing. Columns in the table, table of the data set, right? So these are all used synonymously. And the reason I highlighted these words or the phrases is because these are PCA is sometimes referred to as factor analysis as well, right? Principal factor analysis and principal component analysis, they all mean the same. So that is a little bit of history on PCA. Now, more intuition. Can we use just one dimension for this two-dimensional data? So obviously, yes, because that's the whole idea of dimensionality reduction. But what is the direction? Which direction does this data like the most? Obviously, not the y-axis, not the x-axis, but a line in this direction. Now, then the question is, how do you find that direction? How do you find this synthetic dimension is what the principal component analysis addresses. Now, what is the statistical parameter that is indicative of direction? The answer again is covariance. So the variance, the data, the covariance is in this direction, right? X and Y are negatively correlated, so the covariance is also negative, right? So again, the key idea here of finding the direction is variance. Where do the points vary the most? That's what we want to capture. Now, I'll ask you a very simple question. See, what is a matrix? Matrix is basically a transformation, right? So when you multiply a vector with a matrix, what happens? It transforms the vector. So vector is a point in space. There are two interpretations of vector, right? One is vector um, um, as a list of numbers, and the other is the vector as a point in space with magnitude and direction. Both mean the same because a vector 3, 4 is same as a point in space with coordinates 3 and 4 with a magnitude of 5, the hypotenuse, the distance from the origin, right? And the direction of tan inverse of 3 by 4 or something like that, right? So both mean the same. So, so obviously when this vector is multiplied by a matrix, the matrix transforms this vector. So the matrix can be considered as a linear transformation, right? So how does it transform the vector? The vector changes its magnitude and direction, right? When it is multiplied by a square matrix. So that is one key idea to remember. So the other idea, I keep repeating this idea, the idea of variance, right? So the like the long ears or the big nose in the caricature, we want to capture the variance in the data. So that is the essence. So now you might be thinking, why not just use linear regression? Why do we even bother about PCA and all that stuff, right? Because the reason we use PCA is because the goal is to find principal components, not just one line. We want to find the hidden features and not just the direction of the spread, right? But there are similarities between linear regression and PCA, which we will cover later. But we use PCA for a deliberate reason. Now, some of the ideas in PCA. Let us explore some of these ideas in PCA. So the first idea is capture as much important information in a data set, but using fewer features. So that is the key idea. Just like in the weight loss diet plan, you still want to capture the important content in the diet. You don't want the person to lose the important constituents in his diet. But we want lesser features, right? Lesser. For that, we come up with this synthetic plan, synthetic features called carbohydrates and all that stuff, right? And the other point to note is that these features are orthogonal. That means they're perpendicular to each other. So you are transforming the feature space from correlated features to entirely uncorrelated orthogonal synthetic features. So just like in the diet plan, the synthetic features are orthogonal. There's absolutely no relation between carbohydrates, protein. They're completely independent of each other. So if you take donuts and what is that, a bagel, there is some similarity, right? Donuts and bagels have carbohydrates and probably some amount of fat. But there is no commonality between protein and carbohydrates. They are orthogonal. They are 90 degrees to each other. So when the vectors are orthogonal to each other, when they are independent, right? They are completely independent of each other. So we are going to come up with new dimensions which are orthogonal to each other. They are uncorrelated, entirely uncorrelated. So basically the idea is that we are coming up with a new set of axes than the original set of axes, right? This new axis obviously has to be perpendicular. But the good thing about this new axis is, like, unlike in the original axis where the x and y are not completely independent of each other, there's some dependence. In this new axis, the dimensions are completely independent of each other. So that is the advantage. And that's what we want also, right? In ideal situation, the axes should be completely independent of each other. But in real life, that's not usually the case. So once we come up with this new set of columns, the transformed feature space, we can drop the least important features so generated. Again, the importance is indicated by the variance in the data. How much variance does the feature capture? For instance, in George W. Bush, probably his mouth, there's not much of variance in his mouth, right? He looks like most other people when it comes to his mouth, right? Whereas on the other hand, Obama varies a lot in his cheeks and his mouth. So the feature mouth captures a lot of variance for Obama, but not for Bush. So those kind of things, we look at those kind of features in the synthetic feature set, not the original feature set, but in the synthetic feature set, we look at those kind of things. And then we drop the less important features. So the result is the original data set is now projected in a fewer dimensional space. So now, if you have observed in the discussion so far, the keywords are variance, orthogonal, and relative importance. So what does that tell you? So variance, orthogonal. So variance indicates that we need to compute some kind of a covariance of the data, covariances of the data. Orthogonal indicates that we want to come up with synthetic features which are orthogonal, independent of each other. And then relative importance. We want to somehow compute the variances captured by the features. So all these things can be accomplished by thinking of covariance matrix, eigenvectors, orthogonal, or eigenvectors are known to be orthogonal for symmetric matrices like covariance matrix. So we'll see what a covariance matrix is, but covariance matrices are symmetric. And then eigenvalues. So eigenvalues kind of indicate the importance, right? So eigenvector can be thought of as in a different way also. Eigenvector can be thought of as the favorite direction of a square matrix. Every square matrix can be thought of as having a favorite direction. For instance, some communities pray facing the east direction. Some communities face the direction of their holy place when they are praying, right? So direction plays an important role in praying also. So just like that, just like people have a favorite direction, the square matrices also have favorite direction, and that favorite direction is given by the direction of its eigenvector. So let us look at the notion of variance and correlation in case you are a bit rusty on that. So for one variable, the covariance is given by this, right? You subtract the mean from each of the values, you square it and divide it by the number of data items, you get the variance. For two variables, it's quite similar. The formula is quite similar, just that instead of just one variable, you have two variables. So if xi is equal to yi, then you get back the variance, right? The same formula for variance. So covariance for two variables is given by that formula. And if x and y are independent, the covariance of the two variables will be 0. If they are directly correlated, the covariance of the two variables will be greater than 0. And inversely correlated, then the covariance will be less than 0. So these are all very fundamental concepts. Now there is a related concept called correlation coefficient, which was given by Pearson, who gave us the same principal component analysis. Now correlation is a step ahead of covariance. Correlation values are normalized, whereas covariance values are not. When you divide the covariance values by the standard deviation, it essentially scales the value down to a limited range of -1 and 1. This is precisely the range of the correlation values. Covariance indicates the direction of linear relationship between variables. So we saw that in earlier also, right? So the points where the data varies the most, the direction where the data varies the most is the direction of the relationship between the variables. Correlation measures both the strength and direction of the linear relationship between the two variables. So those are the fundamental concepts of variance, covariance, and correlation for two variables. But what if there are more than two variables? For three or more variables, we have what is called as a covariance matrix, which is basically the pairwise covariances of the variables. So this is an example for three variables. The diagonal is simply the variances of the variables, and the remaining capture the covariances. An important thing to note is that this is a symmetric matrix. Why? Because the upper triangle, upper right triangle of the matrix is same as the lower left triangle. So the upper left triangle and the lower left triangle are identical. So that's why that is the definition of a symmetric matrix. Right, so covariance matrices are symmetric. Now, if the data is already mean adjusted, that means the mean is already subtracted from the data, like this numerator of this variance is already done. What is the covariance? So for x, the mean is subtracted from all the data, and y, the mean is subtracted for all the data. So what is covariance in that case? The covariance is simply the dot product of the features, right? Which are, of course, mean adjusted. The mean adjusted dot product of features is the covariance. So that's a very important point to remember. The reason I mentioned that is because this concept is used in support vector machines, for instance, where we compute what is called as a kernel matrix. So kernel matrix, so X is our data set. In most of the textbooks and research papers, X is written as a set of data items. So X1 is one column, one feature, X2 is one feature, X3 is one feature, and so on. So X1, X2, X3 are the columns of X. So X is a row vector of data item vectors. So then, in this case, the mean adjusted covariance matrix, like I mentioned earlier, is the dot product of features. So the kernel matrix is given by the X transpose times X is the kernel matrix. And the corollary for this is the covariance matrix is given by X times X transpose, right? So they are very related. Covariance matrix and kernel matrix are very related. They basically are kind of dot products or inner products. If it is just real numbers, it's dot product. But if the numbers are both complex and real, then it's inner product. Now let us talk a little bit about eigenvalues and eigenvectors. Like I mentioned, a matrix transforms a vector when it is multiplied by the vector. It changes the magnitude and direction. So it scales the vector and it rotates the vector. However, for any matrix A, there are some favored directions, uh, like mentioned earlier. So in this favored direction or favored vectors, the matrix does not change or does not rotate the vectors. It only changes the scale. And no other vector when acted by this matrix will get stretched as much as this eigenvector, right? So all the transformational energy in the matrix is applied in changing the magnitude of the vector and not in the direction. All the energy is focused only on the magnitude, not the direction. By the way, eigen is a German word, and in German, eigen means characteristic, right? So eigenvectors are characteristic vectors. So, and then what are eigenvalues? Eigenvalues are scalar values that represent how a linear transformation stretches or compresses space, right? In the next slide, I'll show you what I mean. But you know that the vector gets stretched, right? The magnitude increases, or it could decrease also. So eigenvalue basically tells you how much the vector got stretched or compressed, right? When the vector is multiplied by a transformation or a matrix. Now, for a given eigenvalue, there are multiple eigenvectors. There could be multiple eigenvectors, right? The set of all eigenvectors corresponding to a particular eigenvalue is called eigenspace. We will also discuss this in the subsequent slide, but I'm just introducing the concepts first. And so if A is a square matrix and lambda is an eigenvalue of A, if there exists a non-zero eigenvector V such that A times V is equal to lambda times V. So A is a square matrix, V is a vector, and when a vector is multiplied by a square matrix of compatible dimensions, you get another vector. And if the vector is an eigenvector, it only stretches by a factor of lambda. Stretches or compresses, either way. If lambda is negative, it becomes shorter. It compresses. So only the magnitude is changed. The direction remains the same. The magnitude of the vector changes, but not the direction. And eigenvectors are non-zero vectors that only change by a scalar factor when a linear transformation is applied. That means when a matrix is multiplied, only the vector changes by a scalar factor, lambda. Direction does not change. Now there are two interesting properties for eigenvectors of a symmetric matrix, which are very useful for principal component analysis, right? So first is orthogonality. Eigenvectors corresponding to distinct eigenvalues are orthogonal. So they are linearly independent for symmetric matrices. So that is exactly what we want, right? We want to come up with synthetic features like carbohydrates and proteins, which are completely independent of each other. There's not a little bit of carbohydrate in protein. There's not a little bit of protein in carbohydrate. So you want to come up with those kind of synthetic features. And for that, orthogonality of the features is very important. And the second property is eigenbases. Eigenvectors can form a basis for a vector space because they are orthogonal. They can actually form the basis for, they can create a new vector space, right? That is exactly what we want. We want to transform the feature space into this new vector space. The columns, the k columns, you remember the k columns in our very first slide. These k columns should be entirely independent of each other. So orthogonality comes in there. And we also want them to be, what was the second property? The second property was we want them to form a new feature space. We want them to form a basis for a new vector space, right? The k columns. So fortunately, eigenvectors give us both. So that's the reason why we use eigenvectors. So once again, to illustrate the concept of eigenvectors, I downloaded this GIF from Wikipedia. So this is a 2x2 real and symmetric matrix, and it represents how the space is stretched or condensed. So the space is basically the plane, space on the plane. And you can see that most of the points are changing direction. And if you focus on one single point, it is changing direction and also the magnitude when a matrix is multiplied with it. But there are some points in this plane which do not change direction. See, if you notice the points on these red lines, these two red lines, you notice that they don't change direction, but they get stretched. The distance is increasing, right? If you just focus on this point alone, it is moving rightward, right? It is getting stretched, but the direction itself is not, direction from the origin itself is not getting changed. So that is the idea. So the eigenvectors of the matrix, the red lines, are the two special directions such that, I mean, in this case, there are only two dimensions. So those are two special directions such that every point on them will just slide on them. They get stretched, but the direction does not change. Whereas all other points, you take any other point, focus on just one single point, it changes direction as well. So spectral algorithms use information contained in the eigenvectors of a data affinity matrix to detect structure. So data affinity, because remember, covariance is basically similar to correlation, similar to kernel matrix, which basically tells you how much affinity is there between two data items, right? So how much love is there between husband and wife can be computed by computing the dot product of their features, right? In vector algebra, in linear algebra, you extract all the features of wife and husband and compute their dot product, and that's how much they like each other. So that's the reason why I sometimes call dot product as doting product. It indicates the love or affinity between two data items. See, people are basically vectors, right? In vector space, when you want to do machine learning on people, each person is a vector in vector space. So the affinities between the people is given by the dot product. So spectral algorithms is a class of algorithms which use this kind of eigenvectors, extract the eigenvectors of data affinity matrices. The reason it is called spectral is because it functions like extracting the spectrum of the data. So prism, what does prism do? It extracts a spectrum of white light. Similarly, PCA extracts the spectrum of the data, the hidden features of the data using eigenvalues and eigenvectors. So the Vibgyor colors, the violet, indigo, those colors are hidden in white light. They are extracted by the prism. The hidden colors are extracted by the prism. Similarly, PCA extracts the hidden features using these concepts of eigenvalues and eigenvectors. You can also think of it as a Fourier series. Fourier series is a slightly advanced concept. We will not go there, but something similar. Now, how do you find eigenvalues and eigenvectors? Typically, this is covered in high school math, but just to be unsafe, just to make sure that you're not lost, I wanted to cover some basics. So first thing is, there's something called a characteristic equation. So the determinant of A, which is a square matrix, minus lambda times the identity matrix is equal to 0. This is called the determinant. So the determinant of this matrix is called the characteristic equation. So A, from the matrix A, you subtract lambda times I. What is lambda? Lambda is basically the eigenvalue. So A is a matrix, square matrix, for which we want to find the eigenvalues and eigenvectors. Lambda is eigenvalue, and I is the identity matrix of the same size as I. So that is the characteristic equation. Now, why is lambda a root of this characteristic equation? The reason is because, remember, the definition of eigenvector or eigenvalue is A times X is equal to A lambda times X, where X is the eigenvector and lambda is the eigenvalue. So when you take the right-hand side to the left-hand side, you get AX minus lambda X is equal to 0, which means A minus lambda I is times X is equal to 0. And by definition, eigenvectors are non-zero. Therefore, because X is not 0, the others multiplicand must be 0. So the determinant of A minus lambda I must be 0. So that is the idea of characteristic equation. Now you solve the characters. We know A, we know I. We just need to find the values of lambda. So you just solve the characteristic equation for lambda and you get the eigenvalues. So to find the eigenvectors, you just substitute the values that you found for lambda in this, and then so V is the eigenvector here. So you just substitute the values of lambda, you get the values of V. Actually, I should change this to X probably, but you get the idea. So solving the resulting system of linear equations to find we'll find the eigenvector. So here's an example, 2 by 2 matrix example. So matrix A is given by 4, 3, 2, 1. Let's see how much time this takes. I want to cover this quickly. Now the characteristic equation is, so lambda times I, you subtract from the matrix A, you get only the diagonal elements will be subtracted from the diagonal, you have to subtract lambda from the diagonal elements. So that's what it means, A minus lambda I. So 4 minus lambda and minus 1 minus lambda is a diagonal, new diagonal. The other elements remain the same. So that means you get this characteristic equation. So that results in a quadratic equation. You can find the roots of a quadratic equation using 2 methods. One is factorization, the other is using the formula minus b plus or minus whatever the discriminant and all that stuff. So you can go that route, or you can do a factorization. For simplicity, I use factorization to get the eigenvalues as 5 and minus 2. Now, how do you compute the eigenvector for lambda is equal to 5? You substitute the value of lambda in the characteristic equation. You get this, and when you multiply the matrix with the vector, you get these two equations. Interestingly, both the equations happen to be the same. They are identical. What does that tell you? So that tells you that there are infinite number of eigenvectors. So solving this system gives many eigenvectors such as v is equal to 2 comma 1. So I'm deliberately choosing corner cases so that you don't get confused when you encounter similar kind of scenarios. Like for instance, you are in an interview, right? Um, so you should not get confused when you encounter these kind of scenarios. Uh, so the eigenvalues are only two, but there are many eigenvectors. So you can choose any x and y. So eigenvalues are more important. So when eigenvalue is -2, we again substitute the values, you get new equations, and this time again, it will result in identical equations and infinite number of eigenvectors like 1 comma -3, 2 comma -6, and so on, right? So in general, how many eigenvalues will be there for a 2 by 2 matrix? Obviously, it will result in a quadratic equation. So there are two roots, so two eigenvalues. 3 by 3, 3 eigenvalues. N by n, n eigenvalues, right? So you get the concept. So if there are n dimensions in the original data set, you will get n eigenvalues for the covariance matrix. So basically, the number of roots of a characteristic equation. Now for 3 by 3, I will not spend a whole lot of time. You do a similar thing. So you come up with a characteristic equation, expand the determinant using cofactor expansion, choose a column and row to expand along. So all that stuff, you know how to do that. I will not go over that. And then evaluate the determinant. And you'll eventually get a cubic equation. The way to solve for cubic equation, solve a cubic equation is again apply a formula, which is very tedious, but I prefer factorization. So the roots are 1, 5, and 20 for this, and eigenvectors can be found like before. So that is the intuition behind, or that's the process of finding eigenvalues and eigenvectors. Now you might be wondering, what if the eigenvalues cannot be found? What if the quadratic equation is not solvable? What if the discriminant of the quadratic equation, characteristic equation, is negative? B square minus 4ac can be negative, right? So what if it is negative? So you might be wondering about that. But the good news is it is not possible for covariance matrices. This is mathematically proven that covariance matrices, which are symmetric, cannot have imaginary numbers as their roots. So there are some special properties of eigenvectors of a symmetric matrix like a covariance matrix. Or if all the values in the symmetric matrix are real. What is a symmetric matrix? The transpose is same as the original matrix. So if they're all real, then eigenvalues and eigenvectors are real numbers as well. See, our covariance matrix is real, right? All the numbers in the covariance matrix are real and it is symmetric, and therefore the eigenvalues and eigenvectors are real numbers as well. Eigenvectors of real symmetric matrix are orthogonal. This is the next property which really helps us with PCA. By the way, these are all proven theorems. I'm not going into the theorem. They're all simple proofs, but I don't want to go into the theorem in the interest of time. And then spectral decomposition. A matrix S which is symmetric can be decomposed into three matrices: Q, lambda, capital lambda, times Q transpose, where Q is the orthogonal matrix. Q's columns are eigenvectors of S. So you find the eigenvectors, put them in Q, take its transpose, multiply Q lambda Qt, um, you get back S. So lambda is a diagonal matrix of eigenvalues of S. So lambda contains just the diagonal, and what are in the diagonal? The eigenvalues of S. So that is called spectral decomposition or eigen decomposition. You can compute the eigenvectors and write the matrix S, a symmetric matrix, as Q times lambda times Qt. So, and all the eigenvalues of a positive, definite, symmetric matrix are positive. So this concept is very important, positive, definite, symmetric matrix. It comes in support vector machines in machine learning as well. Uh, Positive, definite, you know the meaning of symmetric, but what is positive, definite? Positive, definite, a very rough way of thinking about positive definiteness is that all its eigenvalues are positive. So that means no matter how you stretch the space using the matrix, no matter what transformation you apply, the outcome only expands and does not shrink or stay the same. The vectors get only stretched. They will never shrink. So that is the meaning of positive, the eigenvector sign. So that is the meaning of positive definiteness. And covariance matrices are often positive semi-definite. Just like the kernel matrices are positive definite, covariance matrices are also positive definite. So that is the idea. So these properties really help us a lot in PCA. Now, I anyway gave the proof for why the eigenvalues of gram matrices are non-negative. So, so gram matrix is also an affinity matrix or a kernel matrix. It can be written as X transpose times X, like we saw in the previous slide. And if the corresponding eigenvector is V, then X transpose X times V is equal to lambda V. By definition, you multiply both sides by V transpose, you get this, and then you change the association. Instead of X transpose X, you make the association with V transpose times X transpose. Now, linear algebra tells you that V transpose times X transpose is X times V transpose, right? You remember from matrix theory. So you just do some manipulation and you will eventually end up with this, and both sides are positive because V transpose V, and see X times V is a vector and V is a vector. So vector transpose times vector is a norm, right? And norm is a distance, and distance is always positive. So both sides, both the products are positive, both the vector products are positive. So therefore, lambda has also to be positive. Otherwise, if lambda is negative, this becomes negative, right-hand side becomes negative. So that's why lambda is positive. So the same thing can be applied for, this is for gram matrices. The same thing, you just replace X transpose X by X times X transpose, you get the covariance matrix. You do the same thing and you can prove that the eigenvalues are non-negative. So other interesting properties, eigenvalues of the covariance. So this I already mentioned. X times X transpose is the covariance matrix, and similarly you can prove that the eigenvalues for covariance matrix is also positive. The gram matrices, so gram matrix, affinity matrix, they all mean the same. X transpose X is the kernel matrix and X times X transpose the covariance matrix. And both of them share the same non-zero eigenvalues. So why? Because of this. So once again, if U is the eigenvector of X transpose X, So you can do some jugglery, and then you will eventually end up in the fact that the eigenvector for both x transpose x and x times x transpose is the same, right? So you can pause the video and glance over this proof a little bit, and you'll understand it for yourself. This proof is very simple. So I'll not spend time on that. Now, coming back to our principal components, how are we going to find the principal components? So the idea is to come up with these the new directions, new axes from the original x and y axis. We come up with this new axis. These new axes are rotated and both rotated and shifted. So the origin shifts from here to here, and the axes are also rotated. Now, when the dot product is 0, we know that the vectors are orthogonal, and which means that there is very little similarity between the two vectors. So when the dot product between wife and husband is 0, it means they are entirely dissimilar. I'll not get into the philosophy of it, but you can draw your conclusions. But I just want to bring some humor sometimes. So the dot product between the principal components is 0. That is the goal of principal component analysis, so that the principal components are entirely dissimilar. They are completely independent of each other. That is what we ideally want the axis to be. We want x and y to be as dissimilar as possible, right? Now, this is just a two-dimensional case. In 2 dimensions, principal one captures the most okay, let me also. So principal component 1 captures the most variance, and principal component 2 captures the remaining variance in the 2-dimensional case. But how about the n dimensions? If there are not just 2, but n number of dimensions. So we are essentially inventing new axes. So these principal components are latent features like protein, carbohydrates in the dietary plan. These are latent features. And in general, only a few directions manage to capture most of the variability in the data. For instance, this feature PC1 is capturing most of the data. Why do you care for PC2? Just drop PC2 and you're still good. It captures most of the information in the data set. So that is the idea. So first is to sort the absolute eigenvalues. PC1 is the direction of the maximum spread or variance. So the direction of the first eigenvector corresponding to the largest absolute eigenvalue, right? So that is the idea of principal component 1. So obviously, eigenvalues indicate the variance that the principal components capture. Principal component 2 is the eigenvector direction covering maximum residual variation left in the data. And it is orthogonal to PC1 based on our theorems in the previous slide. PC3 will capture the maximum spread left in the residual variance. So after PC1 and PC2, PC3 captures the remaining variance. And PC3 should also be orthogonal to PC1 and PC2. All these directions are orthogonal. So you repeat, if there are n dimensions, you keep repeating. Now, like I mentioned, the observation is that PC1 covers most of the spread, most of the variance. PC2 is almost redundant. So PC2 can probably be dropped without losing significant information that the data conveys. Right? So that's what we do in principal component analysis. Now, how do we express the equations of the new axis in terms of the old? So the original features are x1, x2, x3. The new uncorrelated features are z1, z2, z3, and so on. Now, PC1, the direction of the most spread, is given by z1 is equal to k11 x1 and so on and so forth. x1, x2, x3 are the original features. So you have to remember one thing, we are inventing a new feature space. So when the coordinates change, the data values will also change, right? So we need to recompute the data items in the new feature space. How do you recompute? By using these equations. A general question for your understanding. How many lines orthogonal to each other can be drawn in an n-dimensional space through a given point, given one of those lines? So you are given one line, one point on that line. And it's an n-dimensional space. How many lines can be drawn through the point orthogonal to this original line? So if you think the simplest case, 2 dimensions, you can draw only one line which is orthogonal to the given line, right? 2 minus 1 is 1. 3 dimensions, how many lines can be drawn? 3 minus 1, 2. Similarly, n dimensions, you can draw n minus 1 orthogonal lines to the original axis. So as many as there are axes. So just to give you, just for your visualization purposes. So this again is very similar to our weight loss analogy, right? Diet plan. So you take, x1, x2, x3 are the original features like donut, omelette. What else is there? I forgot the food. I'm a bit frugal in eating. What is the other? Most of them, fruits, say fruits. So the dietitian will tell you, you take this many grams of bagel, this many grams of uh, uh, whatever it is, egg omelette, and so on and so forth. And then tells you that your number of carbohydrates will come from this proportions of these foods. Similarly, Z1 is like your carbohydrates, Z2 is like your proteins, and so on and so forth. So the dietitian is going to tell you that this much carbohydrates will come from these portions of the food. So that is exactly what we are doing here. K11, K12 are basically the portions of carbohydrates, portions of protein, etc. Right? So K11, K12 are basically the weights that we assign to the original features to get the new synthetic features, right? Now, how are we going to find K11, K12, K1M, and so on, right? Any guesses? So most likely you would have guessed that K11, K12, K3, K13 is the first eigenvector of the covariance matrix. Similarly, PC2 is given by K21, K22, and all that stuff. K21 times X1 times. So what are K21, K22, K2M? Once again, your guess is right. They are the numbers in the second eigenvector of the covariance matrix. So on and so forth. So that's how you get the new features, the synthetic features. These PC1, PC2 are all synthetic features. The principal components capture all the information in the original features. So far, there is absolutely no loss of information till now. The entire information is captured, just that we are changing the coordinate system, right? Now comes the dimensionality reduction. Usually, the first few PCs capture most of the information. The rest are redundant. So if so, we keep the first few and drop the rest. So resulting in dimensionality reduction, right? So how do you determine how much variance is captured by each principal component? You come up with something called a creep plot. You can do this in Python. There's a Python package. You don't have to sweat about it. The scree plot, the x-axis, I mean, there are different types of scree plots, but this one on the x-axis is the number of components, and the eigenvalue, sorry, the component number is given on the x-axis, PC1, PC2, PC3 is on the x-axis. And on the y-axis, you have the eigenvalues. We know that eigenvalues indicate the variance or the relative importance of the principal components. So it tells you how much the eigenvalues on the y-axis. So now you can easily see that most of the variance is captured by the first three principal components. You look at the red line. So the remaining eigenvectors capture very limited variance. So you can just be contented with the first three components in this case. So this scree plot idea was given by Raymond Cattell in 1966 in his paper called the scree test for the number of factors. So scree test is basically the procedure of finding statistically significant factors. We already talked about what the y-axis represents and what the y-axis represents. So, in this scree plot, you can easily see that the first three principal components capture most of the information, most of the variance. Subsequent principal components capture progressively smaller amounts. So this helps us determine how many principal components are necessary to retain a significant amount of information from the original data. So that's it. That's how you reduce the dimension. You retain the first three principal components, drop all the remaining 9 principal components. So that's the idea. So the process, to sum up, the process is basically, first is you standardize. So you do scaling and you also make it unit variance. So that means you subtract the mean of the data from X. This is a standard procedure. There's nothing new to PCA. Any machine learning process you'll have to do this. So you subtract the mean and then divide the value by the standard deviation to get unit variance, data in unit variance. And so that's the first step. The next step is compute the covariance matrix for this new standardized data set. So you examine the joint variability of the features, the affinity between the data points, like so if the data is about the students in the class, then this covariance matrix kind of indicates how much each student likes the other student, right? Or the similarity between the students. So that's the second step. The third step is Eigen Decomposition or the spectral decomposition, compute the eigenvalues and eigenvectors for the covariance matrix. So you basically factorize the covariance matrix into eigenvectors. Eigenvalues represent the amount of variance explained by each eigenvector. We saw that before. And then comes the dimensionality reduction. We reduce the dimensions based on explained variance, which is indicated by the eigenvalues. And from there, you transform the features. Remember, we end up in a new coordinate system, so you need to recompute the data items. From the original data items, you compute the new data items. Project the original data onto the selected principal components to create the transformed data. So that is the next step. So how do you do that? So you multiply the original data matrix X by the matrix of selected eigenvectors. Remember, the coefficients are basically the eigenvector, the elements of the eigenvectors, right? The coefficients of the original features. So that's what we do to get the new features. So this results in a lower dimensional representation of the data that preserves most of the variance. So that is the process. So let us look at a small implementation. So we have a small data set with just 2 features, that means 2 columns in the table and 5 rows, 5 observations. So for space, I just write the table like this, but you understand, right? Uh, the columns are the features, and each vector is basically an observation. First step is to standardize, so calculate the mean and standard deviation for each variable. So in Python, you just write this statement, and it gives you the mean. So 4.0 and 5.2. Then you compute the standard deviation, again using a call to a method in Python. Then you apply the z-score normalization, which is x minus mean and all that stuff. You get the standardized data. You converted this data set into this data set by standardizing. So that is the first step. Now, if the original data was the green points, the standardized data will make it, remember, unit variance and mean adjusted, right? So that's the reason why the new data points are in a compressed space. But remember, the relative distances and the directions are preserved. So the other way to look at it is that the dimensions are scaled and shifted, right? So that's what happens with standardization. They're not rotated, but scaled and shifted. So that's what happens with standardization. Now, what is the next step? The next step is computing the covariance matrix. This again can be computed by first transposing the matrix and then computing the covariance matrix using this method. So this is the covariance matrix. So you have to transpose because remember the array is slightly different, right? It's not the direct matrix, it's inverted, it's a transpose. So you have to transpose it again to get the actual covariance matrix. Then computing the eigenvalues and vectors is directly calling this method in the linear algebra package, in the NumPy package, linear algebra class. Just call that method, and then you get it spits out the eigenvalues and eigenvectors. You sort the eigenvalues to determine which principal components capture the most variance, and then choose the top k. In this case, there are only two features, so just to choose the top feature as the principal component. So you get the first principal component and project the original data to the selected principal component. So you transform the data using the dot product. Remember, we had to multiply the vector with the original features with the first eigenvector. So that's what we are doing here, and you get the first principal component. So as you can see, the values are all changed. So the transform data now has a single dimension, just one dimension, probably the x-axis, representing the projection of the original data onto the principal component. The lower dimensional representation captures the most significant variance in the data. So the original data is these green points. After standardization, they become the orange crosses. Now, when you do all the PCA, when you apply the PCA algorithm, the data becomes like this. The only difference is that I use the same coordinate system for all the points, all the transformations, which kind of can be misleading because this is not the same x-axis as the original data's x-axis. This is a different line. This x-axis probably is along this direction. The light green points are along this direction. But the related distances are more or less preserved, as you can see. So these distances are more or less preserved even in the single dimension. So that is essentially the idea of principal component analysis. Now, remember I told you that this is quite similar to linear regression. In fact, in the one of the first slides, beginning slides, an intuitive question could be, why not just use linear regression, right? So there's a lot of relation between PCA and linear regression. Both are linear methods. So in linear regression, what we do is minimize least squares, right? These are all the red dots are the points, and we minimize the least squares, the distances of the points from the line to determine the line. So whichever line gives you the least sum of squares of the distances is the best fit for the points. So that is the idea of linear regression. Now, what are we doing in PCA? In PCA, we are maximizing the stretch of the projection. So this point from the distance of this point from the origin is maximized. So the linear regression, we are minimizing this distance. In PCA, we are maximizing this distance. And due to Pythagoras theorem, minimizing this distance is same as maximizing this distance. You can see, you just pull the point downward, this stretches, right? Right, so minimizing this side is same as maximizing this side, hypotenuse. So PCA maximizes the hypotenuse, linear regression minimizes the projection, right? So essentially both are equivalent. So the eigenvalue lambda tells whether eigenvector x is stretched or shrunk or left unchanged for that matter when it is multiplied by the covariance matrix. We prefer the directions which maximize eigenvalues. In other words, maximize the stretch, right? So this is quite equivalent to linear regression. So that's the idea. Now a question for you. How can we reduce the dimensionality of this data set? So the data set is pretty much scattered everywhere. So the answer is we cannot. So distances are not so meaningful. The variance of these distances, pairwise distances between points is almost zero, like in high dimensions. So this is not a good candidate data set for PCA. Now, PCA has been applied for many applications. So my student, my MSDS student, Farouzan, and I used PCA for misinformation containment, information and misinformation. So a significant use of PCA is to visualize high dimensional data in a low dimensional space. Typically 2 dimensions, right? The low dimension space just has 2 dimensions for visualization. So this can be really helpful for understanding the relationships between the variables in the data. So we used it for misinformation, understanding misinformation. So a lot of research papers have claimed 100% accuracy in misinformation containment using machine learning algorithms. But when we actually visualize the data set and also applied some machine learning algorithms, the observations that we made are quite different. The observation that we made, very pertinent to PCA, is that there are no unique clusters in the space. So there are 3 classes of information in the data set. So there's false information, there's true information, and then there's pants on fire kind of information. 3 different classes of misinformation, right? Or information or misinformation. So we observed that there are no natural clusters of these points. They're all together. All the classes of information are together. They're all clustered together. Which means that it is very hard for machine learning algorithms to distinguish between misinformation and information. So that was the conclusion that we made in this paper. And there are more interesting applications also. And one of the more interesting applications is that of Eigen Faces that was published in 1991. So given a set of images of faces of people, what are the features? The obvious feature is pixels, but this paper uses bytes in the images, just bytes in the images. They don't go by pixels, instead they go by bytes in the image. So image is basically bytes, right? The bytes of any data is basically bytes, and it's in raw form. So features are bytes in the image file, and image data is highly nonlinear, obviously, because there's no way the data can be put on a single line. But still, it was observed that PCA performs pretty well on the face image data. So they use PCA for recognition, image recognition, face recognition. Very interesting, right? So the training of the model is basically computing the eigenfaces. What are eigenfaces? Eigenfaces are basically eigenvectors. Eigenvectors of the bytes in the images, when plotted, look like faces. So these are the eigenfaces. They look like faces. The byte values in the eigenvectors look like faces when plotted. That is the reason why these eigenvectors are called eigenfaces. So if you look at the principal component, the first eigenface, this is the first principal component. It captures the variance common to most of the faces in the given image set, right? It captures some amount of hair, then the face cut, and all that. The commonality is captured in the very first PC. Now, specifics like eyeglasses, mustache are captured by the components towards the end, like this eyeglasses and other things are captured towards the end. So, because only a few of these images seem to have them, right? So that's the reason why it's lesser variance. Eigenfaces kind of function like basis vector, just like eigenvectors are basis vectors, eigenfaces are basis vectors. So what does that tell you? That means that all images of faces can be expressed as a combination of these eigenfaces. Any new vector can also be generated using these eigenfaces. So that is the power of unsupervised learning, right? Generative artificial intelligence is about generating from existing distributions of data, right? So that is the power of unsupervised learning. Using unsupervised learning, you detect hidden patterns, and using the hidden patterns, you can generate new data. So in this case, new faces. Now each phase that you can generate is a weighted sum of the eigenfaces. Now you might be wondering, all this is good, but how can we do face recognition with this? It is simple, right? You just apply a KNN algorithm, K nearest neighbors. So you are given a new face, project it into this new feature space of eigenvectors, and then see which face comes closest to this new face. And that is the classification for that face recognition, right? So that is the idea proposed in this paper, very interesting. And another paper in 2011 came up with this idea of eigenviruses. See, anyway, we are processing bytes, right? So why not do do PCA on the bytes in an executable file? So they use bytes in the dot text section. If you know Unix file format, there is a dot PSS, I forgot There's headers, then there's dot BSS, there's space for stack. BSS, I think, is for stack and things like that. Dot text section contains the executable code. So these researchers use the executable code in the dot text section, the bytes in the executable code in the dot text section as original features and did a PC on that. So, but remember, one thing is they should be of the same size. So there must be, the executable should be of the same size. So just like for faces, they pad zeros so that all the vectors are of the same size. All the viruses are of the same size. So they do a PC on that, and then a very interesting classification. You can do classification of viruses. Eigenviruses are vectors that span across most important features in the same virus files. So these are all virus files, infected files. And then Euclidean distance used to find the nearest neighbor for classification of the virus. So which virus is present in the file can be identified by using a KNN algorithm, just like in case of Eigen Faces. So there are many such applications of PCA. So Eigen Voices is the application of principal component analysis for speech signals. There are a couple of papers using Eigen Voices. Then Eigen Hands is hand gesture recognition using principal component analysis. There's a paper on that. Then Eigen Gestures. So in general, previously the paper only captured hand gestures, but any gesture can be captured or classified or recognized using PCA, using similar techniques. Eigen textures, tensor textures, paper for image-based rendering. Then Eigen images is a more general concept for compression and representation using principal component analysis. So it's a very simple technique, like just high school math, and you can do such wonders using all this. This high school math is what we covered so far. Now, how do we find the principal components of nonlinear data? So there's a helical data set. So data are generated from one-dimensional helical loop embedded in three-dimensional, and then some Gaussian noise is added. Then you generate this kind of a data set. This is from a paper published in 2012. So the nonlinear principal component is plotted as a red line. So the red circles, these are all concentric circles. Sorry, these red circles, sequence of red circles show the projections of the data. The data is the blue dots. So this is an interesting paper for nonlinear data. So the other kind of nonlinear data is in the MNIST dataset, Modified National Institute of Standards and Technology Database. So we all know NIST, right? National Institute of Standards and Technology. They came up with this dataset called MNIST dataset. It's a very popular dataset. It contains 42,000 labeled grayscale images, each of 28 by 28 resolution, pixel to resolution. These are all handwritten digits from 0 to 9. So there are 42,000 labeled images, and there are 28,000 unlabeled test images also. These images can be used for testing purposes. So the goal is to use the dimensionality reduction to visualize these images in 2 dimensions. So obviously this is a nonlinear data, right? Highly nonlinear. So let us see how PCA performs on this. So when you apply PCA on the labeled MNIST data set, you observe that it does perform pretty reasonably well. See, all the light blue, what is it called? Copper sulfate blue is 1 digit, 9, right? So all the 9s are put together and all the 3s are put together. Red ones are 3s. So PCA does a reasonably good job, right? Similarly, the zeros are greens, they're all together. It does a really good job, but not, there is some intermingling of the numbers. Because it's labeled, we are able to see the colors very clearly. And we see that PCA does a pretty reasonable job in visualizing. But a better algorithm is what is called as multi-dimensional scaling. So this is how MDS performs on labeled MNIST handwriting dataset using just the first two principal components. So MDS works like a map maker for data. So it tries to map the data using distances, right? So it uses distances to navigate the hidden relationships and patterns in data, right? So there's a very nice visualization. Anyway, I'll show this. I'll come to this visualization later. I'll save that for the last, but there's very nice visualization of this. So that is MDS. It still does not perform well. MDS is basically a spectral method that preserves a pairwise distances between data items. It aims to preserve the original distances as much as possible. And at the same time projects the data into a lower dimensional space. In this case, just the 2 dimensions. For MNIST, we saw it in 2 dimensions. It still uses Eigen Decomposition. So instead of covariance, it uses the pairwise distances. The matrix is not covariance matrix, but instead it's a pairwise distance matrix. Anyway, it's these are all affinity matrices. So the concept is very similar to PCA. But instead of covariance, it uses distances. So why did it perform not all that well is the question, right? So what is the problem with this approach? Remember the problem with distances? Distances become less meaningful in high dimension space. High dimension space, the distances become less meaningful. So relying on distances alone may not be a good idea, but t-distributed stochastic neighborhood embedding, called abbreviated as t-SNE, uses the distances as well, but it uses a better way of dealing with the distances. What it does is, see, I'll give you a simple example, right? I am currently in India. I traveled from California, San Jose, California to India, a place called Hyderabad in India. So for this travel, what matters to me most? The distances within places in Hyderabad and the distances within places in San Jose, or the distance from San Jose to Hyderabad, right? Obviously, the local distance is what matters to me the most. The distance between San Jose and Hyderabad hardly matters, right? So that is the idea used in t-SNE. So it models the probability distribution of pairwise similarities between data points in both the high dimensional space and the lower dimensional space. But it minimizes the divergence between the two probability distributions. So it tries to make sure that the distributions in the high dimensional space and the low dimensional space are minimal, are similar. So this ensures that similar points are projected near each other in the lower dimensional space. A result of this is that the t-SNE algorithm does not preserve global structure very well. So the distance between San Jose and Hyderabad is not preserved so much. So preserves only the smaller pairwise distances between the data items. So we can think of them like neighbors within a group. All the places within Hyderabad or San Jose are neighbors, right? So only those distances are preserved, not the long distance. So it is very good at identifying clusters and anomalies because of this. And the visualization of high dimensional data can be facilitated better. So if you put the places in Hyderabad and San Jose in the same map, it's going to be difficult to in making out the place in these cities, right? Instead, if you shorten the distance between Hyderabad and San Jose and represent them in the same map, it makes much better sense. So that is the idea in t-SNE. But the downside is that it is not good at preserving global distances like PCA does. PCA, all distances are treated uniformly. The advantage is that it handles nonlinear relationships among data very well. And it is computationally intensive because you're computing a lot of distances. And then there are some stochastic elements. So that means there are hyperparameters which will impact the performance of this algorithm. So initialization, then it uses to minimize the divergence between the probability distributions. It has to optimize, right? It has to use an optimization algorithm. And the algorithm uses stochastic gradient descent. And because of the stochastic elements, it's highly configurable using hyperparameters and obviously is non-deterministic. So you'll not end up in the same plot each time. The plot could change, the mapping could change, the visualization could change. So if you apply t-SNE on labeled NS data set, you can see the clusters are brought out even more clearly in the first two components. So different shapes of the same digit are also identifiable. So within 9, the difference in the shapes are also identifiable. This 9 looks a little different from this 9, right? So even that level of differentiation can be made using t-SNE. So that is the reason why t-SNE is most often used for visualization of nonlinear data. So unlabeled, if you remove all the labels from the MNIST dataset, it will still perform well. So as you can see, t-SNE performs really well even when it is unlabeled. Anyway, labels don't matter for the dimensional reduction. So now the problem with distances with the previous algorithms is that the distance measured was Euclidean. But when is Euclidean distance applicable? Euclidean distance is applicable only when the points are on a single hyperplane, right? The assumption is that the points are all on the same hyperplane, which is very unrealistic because the data, the way we started this talk is by saying that data has a hidden structure, and it is very unlikely that the hidden structure is always a plane, a hyperplane, right? Instead, the data usually resides on a manifold, right? A manifold is a special type of curved surface that locally feels like Euclidean space. So you take all the small checks, small squares or rectangles on this donut shape, torus. Each of them is basically can be visualized as a Euclidean plane. So within that square, the distances can be Euclidean. But in the uh, the overall space is not Euclidean. It is more like a manifold. So from this Uh, so from the bugs, you can see this beetle or bug or whatever it is that is going around the shape, right? From the bug's perspective, the world feels flat as it moves around the surface. But if you zoomed out, you will see the curvature of the torus shape, right? So that is the idea. The concept of geodesic is one of the foundations for geometric deep learning. So this distance between, the idea I'm trying to convey is that the distances are no longer Euclidean on a manifold. There's a special name for the distance, and that name is called geodesic. The distance between 2 points on a manifold is called the geodesic. It is the shortest distance between 2 points on a manifold surface honoring the shape. So this is a central idea in what is called as geometric deep learning. And there's also a dimensionality reduction technique called isomap, which computes geodesic distances directly on the manifold on which the data is supposed to reside. So isomap, just like MDS, uses distances, but in this case, the distance is not Euclidean, but instead it's a geodesic distance. And then it uses some graph algorithms, typically the Floyd-Warshall algorithm that is commonly used in graph algorithms. Commonly used graph algorithm is used for isomap. But the problem is that calculating geodesic distances can be slow, particularly when the data sets are big and high dimensional. Calculating geodesic distances is computationally very expensive. So that's a very big downside. And if the data points are very close together, estimating the geodesics can make it difficult. So that is the other dimensionality reduction algorithm called isomap used for visualization. Now, in general, there is something called as manifold learning, right? So manifold is basically, like I mentioned in the previous slide, it's a surface. It's not a plane, but it's a surface. So in this case, there is you can see an S-shaped surface. It's a two-dimensional manifold in three-dimensional space. PCA identifies, when you apply PCA on this kind of data, it identifies the three colors, three principal components within the data, but it is not able to capture the curved dimensions, right? Projections on the first two PCA components result in a mixing of colors. As you can see, the colors are all not clearly separated. Whereas if you use manifold learning like isomap, or there's another manifold learning technique called LLE, which preserve the local structure when projecting the data, preventing the mixing of colors. So LLE stands for locally linear embedding. So that's also similar to isomap, uses it preserves local structure very well, and that you can clearly see the advantage that these algorithms bring out. There is an even interesting algorithm called UMAP, which is from a paper. Anyway, this paper is not cited on the slide. But anyway, UMAP performs very well in both ways. It balances preserving local distances and also the global structure. Remember, t-SNE preserved only the local structure, not the global, but UMAP does well in both local and global structure. So it learns a low-dimensional manifold that approximates the data. So it assumes that the data resides on a manifold and tries to find that manifold. So the UMAP reducer is able to, the other advantage is UMAP technique can be used in both supervised mode with labels or unsupervised mode without labels, right? It just like t-SNE, it uses graphs. It constructs a k nearest neighbor graph, and the distances are defined based on how reachable different nodes are through the graph. That means the neighborhood concept comes into picture in UMAP. So essentially builds a topological representation of data, preserves both local and global structure based on manifold learning and graph theory, can capture, just like t-SNE, it can capture nonlinear relationships in data, and it is computationally efficient compared to t-SNE. So when you apply UMAP on MNIST images, you can see that it does very well on the MNIST images. So UMAP is a very powerful technique that we used in analyzing multi-language, multi-region music tracks. This is the paper that I mentioned at the beginning of the talk. I presented it on the 4th of January, that is 2 weeks back. This is the work done with 2 high school students, one in 9th grade and the other in 11th grade. So, what we did was we converted the music tracks into a good representation using MEL spectrograms. And then we plotted those points and applied PCA, t-SNE, and UMAP. And then to determine whether the representations capture subtle insights, like whether the artist is veteran or a newbie, and whether the language is Marathi or Nepali or Nagamese. Can those kind of subtle features be identified in lower dimensions using these techniques? That is the research question that we answered. That is one of the research questions that we answered. And as you can see, PCA, t-SNE, and UMAP all do really well on the data set. UMAP does really excellent when in a supervised mode. You provide the labels also to UMAP and you get very clear distinctions. You can distinguish the veteran status, you can distinguish the singer, you can distinguish the language. There are a lot of subtle factors that you can distinguish using UMAP. So many algorithms for nonlinear dimensionality reduction, we just covered just a few. In fact, I will talk about it towards the end because my Zoom sharing is a bit limited. I don't have a second screen. I'll show the screens later. But so the Swiss roll projected on 2 rolls in a 2-dimensional space will look like the unrolled manifold. So the left side is a 3-dimensional data set of 1,000 points in a spiraling band. This is a very famous data set called Swiss roll with a rectangular hole in the middle. And on the right side, the same data set in the original 2D manifold used to generate a 3-dimensional data set. So this is a common data set used for nonlinear techniques. So there's a whole taxonomy of dimensionality reduction techniques. This paper is from 2009, but there are many more than this. Many more new algorithms have come after this, which it does not capture. So there are 2 classes. One is convex and the other is non-convex algorithm. In convex, there is a spectral, which use Eigen decomposition, and non-spectral or sparse spectral, which use different kinds of methods. So you can see the distances used. So as you can see, ISOMAP uses geodesic, and Kernel PCA uses kernel-based distance, so on and so forth. So there's a whole class of the multiple classes of algorithms for dimensionality reduction. So convex techniques, essentially, as the name indicates, optimize an objective function, a convex objective function that does not contain any local optima. So that is the idea behind convex optimization. The more recent ones use graph theory mostly, and the non-convex techniques optimize objective functions that do not contain a local optima, right? Just like machine learning, convex and non-convex optimization applies here also. Okay, so that's the taxonomy, and I just want to cover quickly about kernel PCA. So kernel PCA is similar ideas, it draws similar ideas from support vector machines. So the idea is to reduce the dimensions, we first increase the dimensions. It's a paradox. So we first increase the dimensions by transforming the nonlinear data into higher dimensional space, just like in support vector machines, right? Then we reduce the dimensions by running the PCA in the higher dimensional space. Now the good thing is, remember we talked about a property, a theorem, that finding the eigenvalues of the kernel matrix is equivalent to finding those of the covariance matrix. We even saw the proof, right? So instead of finding the eigenvalues of the covariance matrix, we instead use the kernel matrix in place of covariance matrix and compute the principal components, the transformed space, right? So the feature vector is now transformed as alpha I times the kernel matrix element, right? So alpha i's are the respective weights or the values in eigenvectors of the kernel matrix, just like before. So that is the idea of kernel PCA for non-linear data. Remember, PCA works only for non-linear data. Kernel PCA works for non-linear data as well. Now there's a nice demo, which I will again show towards the end. I just click and save it. So that pretty much concludes my talk. My information is on the website, San Jose State University's website, and I'm on social media. Please feel free to connect. And before going to questions, I just want to share what? Share my Chrome browser to show you some demos. So this is the visualization. This is a very nice visualization using TensorFlow. So I can choose the data set. In this case, this is word to vec data set. As you can see, each point is a word, like this point. I hover on that point. So I hover on this point. These are all words. Words plotted using their embeddings. So denote is this word. This is switched. So all these words are now plotted in the space, in the vector space. They are labeled by word, and I can choose a color map. Now, I can choose the visualization technique. So this is using PCA. So this is using PCA. I can choose t-SNE and see how it looks. Or t-SNE will take time because of the computation of lots and lots of distances. I should have chosen a different data set. So t-SNE produces a different kind of data set, a different kind of plot. Actually, let me do this. I'll choose a smaller data set. Iris is probably the smallest data set, right? Iris is a data set of flowers, labeled by class and color by petal length. Let us do petal length. So when I do a PCA on the iris dataset, I can hover and it will tell you the kind of flower it is. So these are all centosas. So these are all centosas, and these are all, what is this? Anyway, this is a different class of flowers, and the color is by petal length. So different petal lengths will have different colors. So that is using PCA. Now let us visualize using t-SNE. Okay, so t-SNE, t-SNE works even better. See, as you can see, centosas are all on one side, and the other flowers are all on the other side. And and how about UMAP? Let us look at UMAP. So UMAP, as you can see, UMAP brings out the distinction even more. So these are all the hyperparameters. I can set the number of neighbors. So I can run the, use the number of neighbors and so on and so forth. So this is a nice visualization of the three algorithms. There's also, oh yeah, the other thing I wanted to show was this nonlinear dimensionality reduction. So this is where I got the images from. This is a Swiss roll data set. And let me see. So the first nonlinear data set principal dimensionality reduction technique is kernel PCA, which we talked. Then using manifolds, Laplacian eigenmaps, isomap, locally linear embedding. So as you can see, there are lots and lots of dimensionality reduction techniques for um, nonlinear data. Even autoencoder, which is based on neural networks, is a very good visualization tool for reducing dimensions. So that's the other thing I wanted to show. And the third thing I wanted to show is this nice visualization that Kola has developed for these algorithms, visualizing MNIST with PCA. So I think I need to click. Anyway, so in this data set, the same thing, labels with labels, was plotted using PCA, and it produced this for this. And then, yeah, the MDS works better than PCA, as you can see here. And this is for Salmon's mapping. This is another nonlinear technique, which also does reasonably well. So the MNIST, when visualized as a graph, looks like this. Distances, Euclidean distance, these are all zeros, these are all threes, and you can look at the distances, and when plotted as a graph, it looks like this. And based on that graph concept, t-SNE groups them for better visualization. And as you can see, the graph-based visualizations are much better. What else? So visualizing in 3 dimensions. So graph model looks like this. MDS in 3 dimensions looks like this. t-SNE looks like this. So that is the idea of dimensionality reduction and nonlinear data, manifold learning, and visualization, and so on and so forth. So that kind of concludes my talk. Let me see if there are any questions on YouTube. Where is that? YouTube. Let me see if there are any questions. We don't see the chat window. For some reason, the chat window is not visible to me. Anyway, so that concludes my talk. I don't see any questions on Zoom either. So any questions on Zoom? So there are no questions, going once, twice, thrice. So thank you for, okay, no questions on the chat. So thanks for confirming. And so that concludes the talk. Thanks for joining. And hopefully we will see you in the next event.